All right, guys, so we've been taking a look at the instantaneous power for various types of loads, in particular resistive loads, also inductive and capacitive loads. I really want to make a quick mention about units, and then I want to introduce a few more definitions. So the first observation has to do with units for real power and reactive power. Now, real power itself, remember by definition, was for the sinusoidal sources, Vm times I times 2 times the cosine of theta v minus theta I. And the reactive power looked almost identical. The only distinction was that rather than having the sine of theta v minus theta I, we had cosine, we had the sine. Now, unit-wise, cosine sines don't carry units. P must have the units then of the voltage times the current, which in SI units would be a volt times amp. That happens to be a watt. Right? So here, the unit for P is a volt times amp, which is a watt. Right? And even though the units themselves for Q they're also a volt times amp, we do not actually call it a watt, right? And what we actually call it is a VAR, right? And in fact, there's not even a dot between V and A. It's a VAR. Now, the big distinction, the reason we make such a big distinction between the units of reactive power compared to those of real power is that real power itself can actually be turned from electrical power into non-electrical power. It actually does have the ability to do a certain amount of work. The reactive power, however, must be taken into account whenever you actually design delivery systems to make sure that for example, like your cables and things like that don't overload and they don't burn out. It's misleading to give them the same unit because reactive power itself, even though it is present, cannot actually do any real work, right? These VARs themselves are being stored within capacitive elements and inductive elements within your circuit. And then they're re-released into the circuit, but they can never actually do any sort of work whatsoever. One other observation that I really want to make here is notice that this difference of the phase constants for the voltage and the current, they show up in these formulas for the instantaneous power. They're pretty important. This also means that they actually have a name, a specific name, which leads me to some definitions. The first definition that I want to introduce is that of the power factor angle. The power factor angle, I'm sure you guessed it, is theta v minus theta I. This also appears both in this cosine and the sine. The cosine is for the real power, the sine is for the reactive power. So there are two other definitions for those. The next one is that of the power factor, which we use lowercase p, capital F to denote. This by definition is the cosine of theta v minus theta I, while the reactive factor, which we denote as lowercase r, capital F, by definition is the sine of this. Now, in general, whenever we're actually talking about a circuit, a system that's undergoing sinusoidal steady state, oftentimes we really do want to deliver real power to the load, which would mean that for ideal loads, the power factor, if it's going to be an efficient system, we would really want to design our systems in such a way that our power factor is as close to 1 as possibly can get. If the power factor, which has a maximum of 1, if it starts getting a little bit too low, then we need to redesign our system in such a way that we can actually raise that power factor to actually start really delivering true power to the load itself. And we'll talk a lot more about this at length as we go through this chapter.